In this video, we're going to talk a bit about rates of change. Now, rates of change essentially still deals with finding the derivative of a function. So let's say, for example, that we just consider maybe like a sphere of which we know that the volume of the sphere is given by 4/3 pi r cubed. Now, what if I was interested in the rates of change with respect to the volume and the radius? Well, what that means is that you would find that the derivative of the volume with respect to the radius is going to be equal to 4 pi r squared. Now, if we wanted to know, for instance, like what radius will give us when the rate of change is equal to, let's say, 2, so we would end up with like what is r such that the volume is equal to 2, and that should be r. So if that was the case, then you would go about solving it algebraically, where you would have 4 pi r squared is equal to 2. What we do from here is we just go ahead and solve for r by dividing by 4 pi on both sides. So we have 4 pi. So what ends up happening is we end up with r squared equals to 1 over 2 pi. Now, what that means is that basically that r is equal to 1 over the square root of 2 pi. Now, of course, if you rationalize this, this will give you the square root of 2 pi all over 2 pi. So this is the radius of which would make the rate of change equal to 2 units. Now, of course, that's 2 cubic units per whatever units that is. So it's like units cubed per unit or something like that. Now, in more or less sense, like when we talk about like rates of change, we like to associate it to, for instance, like linear motion. So let's imagine that we're alongside the coordinate axis, and we go ahead and we consider that we have 2 points essentially. We have that right here, maybe you have t, and then right here, maybe you have t plus h. Okay, well, I can define, for instance, a function that we'll just call like s of t. Okay, so s of t is more or less like the position. So, for instance, if we go ahead and we look at t and we look at t plus h, well, we can actually look at the difference between the two. So we have that that would be our delta t. Now, of course, this would give us that this would give us that essentially we're just looking at the change in s divided by the change in t. So that would be s of t plus h minus s of t, all divided by t plus h minus t, but that's actually just going to give us h. Now, notice that the top part of this actually equals the displacement. Okay, now, interestingly enough, if we go ahead and we take the limit as h approaches 0 for our position function, we have that basically this gives us more or less the exact same thing as we can relate our derivative to. So we have that this actually would equal what we call the velocity, because essentially we have that this is more or less like distance over time, so that's going to be the velocity. So this was given by taking the first derivative with respect to t. So we have that basically the first derivative of the position function is velocity. Well, in that case, we can actually apply the derivative of the derivative. So that means that the second derivative with respect to t, that's going to be just the derivative of the velocity. So that's going to be the derivative of the velocity, which is equal to acceleration. So we have that basically you have acceleration that's from the second derivative, and then you have that the velocity is from the first derivative. Now notice that, for instance, that the speed is actually equal to the magnitude of the velocity at time t. So in that case, like if we have that there was a descension of 50 miles per hour, maybe going south or something like that, then in that case you would still know that, okay, yeah, it's going 50 miles per hour, even though like you would technically have like a negative sign, for instance. Now, one thing of which that we can use these derivatives is, for example, like Galileo's formula, where you have like S sub t is equal to negative 1/2 g t squared plus v naught t plus s naught. So like if I take like the first derivative, this gives me that I end up with negative gt plus v of 0. If I plug in 0, then I get basically the initial velocity. So v of 0 is the initial velocity, whereas like s0 was the initial height. But if I go ahead and I take the derivative again, well, I get negative g, which is basically equal to the acceleration. Now, in any case, we have that g is actually going to be equal to 16, not 16, but 32. So we have that that's going to be either 32 feet per second squared, or we have that that's basically just going to be, uh, mm, let's see, that should be 9.8 meters per second squared. So in that case, like we have that, the first derivative gave us the velocity, and the second gave us the acceleration. Now, when you get to like, say, for example, like Cal 2, and you're told that, a ball is flying, then you know that the acceleration is negative 32 feet per second squared, or 9.8 meters per second squared. And then you would kind of work your way backwards, like if you wanted to know like the position. But you would have to have known the velocity, the initial velocity and the initial height, for instance. Now, one way of which that we can look at this, for instance, is just taking an example. So like let's say that you have an example where we just look at a position function defined as follows. So we have t to the fourth minus 4t cubed plus 4t squared. So let's say that we just want to find the derivative. So s prime of t is equal to 4t cubed minus 12t squared plus 8t. But if I go ahead and I take out like 4t, this is equal to t squared minus 3t, and that's plus 2. Now notice that you can furthermore reduce this even more by factoring. So you have t minus 2 and you have t minus 1. Now what this basically means is that these are the values, like if we were to set these to 0, that the velocity is at a stop. So here we have that s prime of t, when we set it to 0, that basically tells us that we have t equals 0, 1, and 2. Okay, well, that's those values that, yeah, that the velocity is at a complete stop. Now, if we wanted to know, like, for example, like, the places of which that it moves left and right, well, then in that case, we would just go ahead and say, let's set up an interval line test of 0, 1, and 2. Now, if we plug in values in between, such as like a half, or like 1.5 or even like 3 back into the first derivative, we would have that basically that's going to tell us whether it's moving left or right. So if you plug in 1/2, well, that's going to be negative, that's going to be negative, but that's actually going to be positive. So we have positive, positive, positive. If we plug in 1.5, well, that's negative and that's positive, so this is going to be negative. Now, in this case, like if we have at 3, basically that's going to tell us that we have, let's see, 3, that's positive, 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 so that's going to be positive and positive and positive. So essentially, we know when it's moving to the left and when it's moving to the right. Now, of course, if I wanted to, I could figure out also like when this function is slowing down, for instance. But we'll go ahead and we'll say that it moves left from 1 to 2, and then it moves right from 0 to 1, and then we have 2 to infinity. Now, if I wanted to know, like, for instance, like where the function uh, might actually be moving, or not moving, but slowing down, it would probably be slowing down like somewhere close to 1, and then it would probably be speeding up like somewhere away from 1, and then it will slow down near 2, and then it will, let's see, it will probably be faster away from 2, but then it'll start to slow down eventually. So that's going to be like something that you can probably try. So try to find the acceleration of the above function and find the intervals where it slows or speeds up. In a way, like if you were to kind of consider like, like maybe like a roller coaster, that kind of goes like this and then like that. Well, you would know that, if, for instance, like that you're approaching this peak right here, that it's going to be very slow as it approaches. And then you have that it's going to speed up like right about here, because now you have that it's constant, but it's going to decrease faster. But then once you get to over here, that's where it's going to slow down, and then it's going to speed back up in this case. So that's like one way that you can kind of think of it. But otherwise, like if you've taken physics before, then this is all just review, if anything. Now, the other thing of which that you will end up looking at with respect to rates of change uh, is, for example, like when the velocity is equal to 0. So, for instance, like if we were to probably like just consider an example, like where we have that s sub t is equal to negative 16t squared plus 96t, and we wanted to know the position, find the position when the velocity is at 0. Okay, so in that case, that's like a two-step process where you would have to figure out that, well, s prime of t is equal to negative 32t plus 96. But if you set this equal to 0, basically you get that t equals to 3. So now at this point, it's just a matter of just plugging 3 back in to s. So you would have s of 3 is equal to negative 16 times 3 squared plus 96 times 3. Okay, well, this is negative 16 times 9 plus 96 times 3. Okay, but what this does is it gives you, let's see, minus 144 plus 1 288. So we have 288, but that just basically just gives you 144. So we have that when the velocity is at 0 after 3 seconds, it's going to be at 144 feet. Now, the other way of which that, you obviously could have approached this is that you could have also thought of it in terms of like the algebra, because essentially we have that if you were to look at the model of like the height of a projectile, in this case, like if you have a function that defines it and it looks like this, well, we know that basically that this is the initial height, but then we have that this is when it hits the ground. But for this point right here, this is where we find like the max. So in any case, like if you were to like find the vertex of the position function, like if it's quadratic, I mean, then in that case, you know that you can actually find it really easily. But here, I didn't actually describe it technically from that perspective that you were looking for the maximum. It just so happened that it was the maximum. Why? Because we have that there was a place of which that the slope uh, was constant, which is like right here. Now, this diagram is not necessarily related to this, but you can still kind of view it that way because you know that it's what we're modeling is basically like the projectile that might be going up in this case. Like it goes up and then it comes back down. So in any case, like we tend to look at these functions. Now, once we like get past this section, basically you're going to be looking at functions with related to time. So like, if you go back to the volume problem, you could actually find, for instance, that dv dt is equal to dv dr, but that's multiplied by dr dt. So in this case, like if I happen to know the rate of change of a of the radius, then in this case, like I would just substitute it in, because for instance, if I know that the radius is has gone from, let's say, like 1.5 inches to 1 inch, well, in that case, I know that dr dt is equal to negative 1/2 inch per, like let's just say like inches per minute, for instance. Then in that case, I know that I would plug this into that equation. But then I also know that dv/dr was equal to 4 pi r squared. So all I would need to do is just plug it in whatever the radius happens to be. So like if we go ahead and we just say when r is equal to 1, when r is equal to 1 inch, then in that case, that would mean that the rate of change of a sphere would be 4 pi multiplied by 1. So we have 1 inch squared, and that's multiplied by negative 1/2. But then this would equal to negative 2 pi. Now, notice that basically it's telling you that the function or the sphere is basically becoming smaller and smaller based on this parameter that, yeah, that it's decreasing at 1/2 an inch per minute. So in this case, this is telling us that this is actually decreasing at negative 2 pi inches cubed per minute. Okay, so that's another way that we can actually relate to rates of change, of which in this case, nicely, that's actually related rates. But that's not until later because that's going to be like applications of rates of change. And then we can look at, growth change, like population, or like the spread of a disease, or even looking at like the modeling of an infectious disease and like how fast it's spreading. those sorts of things, because basically the rates of change is exactly what you think it is. It's just like the change of the function divided by time in this case, or yes, so it's divided by time, because it's telling you like how much it's changing per units of time. Okay, so that's going to be it. So next you're going to be looking probably at implicit differentiation. And then furthermore, you'll be able to then move on to rates of change with respect to time.